Let's say JayP wants to connect to YouTube.com over the public internet. Before any communication occurs, some concerns will arise. How can he verify that he is indeed communicating with YouTube? How can JayP know that no one has intercepted his message? Also, how can he be sure that no one altered the message? Well, let's tackle each problem separately. In this video, we will focus on how to verify the identity of YouTube. First of all, JayP should verify the identity of YouTube. For that, he needs YouTube's public key. The public key represents YouTube's identity, and will later be used when explaining key exchange algorithm. The problem is, attackers have come up with ways to intercept a request from one computer to another computer on the internet and launch a man-in-the-middle attack. With this kind of attack, our attacker Chatty would inject his own public key and have JayP think he is communicating with YouTube, while actually he is communicating with Chatty. Let's visualize it to better understand. Notice that JayP's request never reaches YouTube. Instead, it gets intercepted and replied to by Chatty. Now you may think, scary, isn't it? Imagine what could be possible with this kind of attack, from stealing personal information such as login credentials or credit card details, to malware distribution or other malicious goals. How then, can JayP be sure that the public key he received comes really from YouTube? That's where digital certificates come in. They ensure that the public key is indeed coming from YouTube, and not from a malicious Chatty. Actually, digital certificates can be used not only for HTTPS, but also for mails, IoT, and VPN. A digital certificate will contain many information. Let's explore the most important ones. First of all, information about the issuer is included. Issuer is the third party which signed this certificate. Some basic information will include the common name, the organization, and the country. Of course, a digital certificate will also include its validity, with two critical fields, not before and not after. The subject is the owner of the certificate and would be YouTube in our case. The subject will contain information such as common name, address, and most importantly, the public key. Lastly, a digital certificate includes its signature. This is the signature signed by the issuer that proves that this certificate is authentic. Let's focus on the signature part because it is crucial in trusting that the public key is authentic. Now let's ask ourselves, who exactly signs digital certificates? Digital certificates are signed by entities called certificate authorities, for example DigiCert, Komodo, Symantec, or in the case of YouTube, Google Trust Services. In a nutshell, certificate authorities are trusted third-party organizations responsible for issuing digital certificates. Certificate authorities have their own public and private keys. From that, let's explain how signatures are made. The previously mentioned information contained in a digital certificate will be hashed using, for example, SHA-256 algorithm. After the hash is generated, the certificate authority encrypts the hash using its private key using RSA asymmetric key encryption. This encrypted hash is the signature of a certificate, and can only be decrypted using the certificate authority's public key. Anyone with the public key of the certificate authority which has signed this certificate can decrypt and verify that the certificate is authentic and has not been tampered. Let's get to it now. The browser will receive the certificate with all information including the signature. When the browser receives the certificate, it will hash all the information on its side using the same hash algorithm, in this example, SHA-256. Then, it decrypts the signature using the certificate authority's public key to have the hash received from the certificate authority. If both hashes match, then the browser can confirm that this certificate is truly coming from the claimed certificate authority. There exists hierarchies for certificate authorities, the root certificate authority and the intermediate certificate authority. These root certificate authorities does not actually directly issue any digital certificates for servers. It only issues digital certificates for intermediate certificate authorities that act on its behalf. The intermediate certificate authorities can either issue digital certificates for another intermediate certificate authority, or for a server directly. Hence, there is a chain of trust, from the root certificate authority to the server. And the browser will need to trust this whole chain. Operating systems come bundled with a trust store, which is a list of trusted root certificate authorities. This list is maintained by the companies that make operating systems such as Apple and Microsoft. They all require a root certificate authority to undergo one or more audits proving their trustworthiness and validity. Now that was a handful of information to digest. How does all of this fit into the picture? Let's visualize the whole process from the start. First of all, let's assume YouTube.com is a brand new startup. Understanding the need to be secure on a publicly available internet, YouTube would have to own a trusted digital certificate and present it to its visitors. First of all, YouTube goes searching for an intermediate certificate authority. Remember that intermediate certificate authorities are middlemen between servers and root certificate authorities. In the case of YouTube, Google has its own certificate authority called Google Trust Services. After picking an intermediate certificate authority, YouTube makes a certificate signing request. The certificate signing request will contain information that will be included in YouTube's digital certificate, such as common name, organization, and most importantly the public key of YouTube. YouTube will send the certificate signing request to the intermediate certificate authority. The intermediate certificate authority will verify the certificate signing request containing information about the owner, also referred to as the subject. Then, it adds field like issuer information, which is information about the intermediate certificate authority, and the validity, then signs all these information as explained previously in the signing process. Now we have a digital certificate. After signing, the intermediate certificate authority will send back the digital certificate for YouTube. YouTube can now attach its new TLS certificate to its web servers. Now JayP wants to connect to YouTube.com to watch fitness videos. When he will connect to YouTube, YouTube will send its own TLS certificate and the certificates of its intermediate certificate authorities. The certificate of the root certificate authority will not be sent because it is available on JayP's operating system. Now the browser will verify the authenticity of YouTube's TLS certificate. YouTube's certificate will include the issuer information, which is the intermediate certificate authority. The browser will hence know that this certificate is signed by Google Trust Services Intermediate Certificate Authority, and will have its certificate. Any digital certificate will contain information, and a signature, as explained previously. And recall that the signature is the encrypted hash of this information. The browser will hash all the information to obtain their hash value. Then, it will decrypt the signature using the issuer's public key, in other words, the intermediate certificate authority's public key. Again, remember that the signature can only be decrypted using the issuer's public key. After that, the browser will compare the two hash values. If they are the same, then this part of the chain is verified, and the browser will move on verifying the intermediate certificate authority, because as explained, intermediate certificate authorities are not trusted directly by the operating systems. Okay, now the browser will verify the certificate of Google Trust Intermediate Certificate Authority. This intermediate certificate is signed by Google Trust Services Root Certificate Authority. Please note that before this step, we could have many intermediate certificate authorities between the end certificate and the root certificate, and for each part of the chain the same verification process will happen. In our example, we will just stick to one. The signature of the certificate of the intermediate certificate authority will be verified with the public key of the root certificate authority, as with the previous example. When reaching the root certificate authority, that's where the chain ends. The root certificate authority, which is self-signed, will be available in JayP's operating system's trust store. That's it. The browser, after this verification, will display a nice-looking lock icon, like the one in your browser. Now it is guaranteed that the communication is really with YouTube, and that it is safe. Before we wrap up, we will shortly explain three main types of TLS certificates. A single domain certificate is designed to secure a single fully qualified domain name. It means that the certificate is valid only for one specific domain and does not cover any subdomains or additional domains. For example, for the domain www.youtube.com, a single domain certificate would secure only that domain and not any other variations like academy.youtube.com or blog.youtube.com. Single domain certificates are ideal when you have a single website or web application that does not require additional subdomains. They are the most straightforward and cost-effective option for securing a specific domain. Next we have a wildcard certificate, which is a type of TLS certificate issued for a main domain and all its subdomains using a single certificate. The wildcard character asterisk is used in the common name field or subject alternative name field to indicate that any subdomain under the specified domain is covered. For example, if you have a wildcard certificate for *.youtube.com, it would secure youtube.com, academy.youtube.com, blog.youtube.com, and so on. Wildcard certificates saves you from having to manage and renew individual certificates for each subdomain. However, it's essential to note that wildcard certificates only cover one level of subdomains. For instance, a wildcard certificate for *youtube.com would not cover academy.blog.youtube.com. A multi-domain certificate, also known as a subject alternative name certificate, allows you to secure multiple unrelated domains within a single certificate. Each domain or subdomain to be secured is listed in the subject alternative name extension of the certificate. For example, Google and other large companies would use these multi-domain certificates. One of the main benefits would be a simplified certificate management. Google operates a lot of web services and applications, each with its own domain or subdomain. Using multi-domain certificates allows them to consolidate the management of certificates for multiple domains or subdomains into a single certificate. This streamlines the process of certificate issuance, renewal, and monitoring. That's it for our quick explanation about authentication with TLS certificates. In our next video we will explain how communication will be encrypted after this step.